Hey, hello everyone. Welcome to this new colloquium from the IAA Severo Ochoa program. It's our pleasure to have with us today Dr. Kalaga Madhav. So thanks for accepting the invitation to give this colloquium. He will be talking about astrophotonics and the MARCOT Pathfinder. So Dr. Madhav will be properly introduced by Dr. Pedro Amado in his host here at the IAA.
Thank you.
Okay, hello everyone. I'm gonna read a little bit of Dr. Kalaga Madhav's bio. He's head of the Astrophotonics at Leibniz Institute for Astrophysics in Potsdam. His department is leading the development of astrophotonic instruments for both ground-based astronomical observatories and space applications, such as compact spectrographs, frequency comms, beam combiners, Maynard line filters, photonic lanterns, adaptive optics, science-grade detector systems, as well as overseeing the technology transfer from astronomy to diverse applications. And since 2018, he's teaching the astronomical instrumentation and astrophotonics during the summer and winter semesters at the Institute of Physics and Astronomy of the University of Potsdam. Well, without any more ado, I give the floor to Dr. Madhav, and he can start his presentation.
Thank you, Pedro. So thank you all for joining, both in person and online. So I'm Kalaga Madhav. My background is from India. I have 24 years of experience working in optical fibers and instrumentation and photonics in diverse applications. And I started exploring applications of photonics and fiber optics in astronomy since 2017 at Leibniz Institute for Astrophysics Potsdam. So this is a photograph I'm showing on the title slide. All photos show a hand holding something. So I want to emphasize the size here. So the goal for me is to decouple the size of the telescope from the size of the instrument. So we know the instrument scales for the size of the mirror. So my goal is to decouple that and see whether we can achieve small, compact instruments for large telescopes. And it could be for both ground-based as well as for space applications. And either is it diffraction limited or is seeing limited. So I would present some topics that we are working on, and also on the MARCOT Pathfinder with which we are working with Colorado. Right. So, okay.
Click on the screen.
Oh yeah, maybe I should click on the screen. Right. There you go. So, little bit of history on AIP, which actually has a very interesting history, which I should share because I think you will appreciate it. So, I focus on the scientific background, and AIP actually has a legacy dating back to 1700. It's very old, and introduction of the so-called improved calendar in Germany, followed by the first patent of the Protestant German calendar in 1700. Moving forward, in 1711, the first observatory in Berlin was built, and also in 1846 is credited with the discovery of the planet Neptune. And this is actually in the logo of the institute. So if you see the logo of the institute, you will see a few stars, and there's one planet there, right? So that's essentially the symbol of Neptune, and the color is coming from the color of the planet. And in 1784, the foundation of the Astrophysical Observatory Potsdam was built. And 1881, the first Michelson experiment was done in Potsdam. And in 1886, Eugene Goldstein discovers the canal rays. And 1888, discovery of the variation of Earth's pole latitude by Kuster. 1888, we have the photographic determination of the radial velocity by Carl. And experiments at AOP, Astronomical Observatory Potsdam, to find the evidence of radio emission by Wilsing and Schneider. And then 1899, the completion of the Great Refractor of Potsdam. It's still functional to this day, and people are welcome to visit it. And the discovery of interstellar matter by Johannes Hartmann in 1904, and Carl Schwarzschild, everybody knows, was the director in 1909. And first use of photographic photometry by Paul Gutnick in Babelsberg. That's where we are right now. And discovery of high temperature of solar corona by Walter Grotrian. And fast forward to 1992, beginning of AIP as we know it today. And 2002, PMAS at Colorado Observatory. 2003, RAVE, AAO, and LBT in Arizona. 2005. And 2006, inauguration of Stella on Tenerife. 2011, we have renamed to Leibniz Institute of Astrophysics. We still fondly call it AIP. And inauguration of Gregor telescope in Tenerife. And then 2014, first flight of Muse. 2015, first flight of Pepsi. 2018, Hubble Everly. 2019, Rosetta. 2020, Solar Observatory. And fast forward to 2024, foremost that has been shipped to Paranal. And it will be installed in the coming months. So I must introduce my group from 2017 to 2030. My group is in the first part of it. That's me and my colleagues here. And of course, we also work very closely with our workshop, and there have been a few alumni who have contributed to the work that you're going to see now. So I must mention their name. Okay. So since we are working in photonics, when I say photonics, it's always linked to fiber optics because photonics cannot work without fiber optics. And we are at first we started exploring the near infrared technologies because that was quickly available and we started working them very fast. And since you work with near infrared from government observatory, we have these windows through which you can see. And we have to work in those windows. And that is JH and K-band. And we actually can see certain concept instruments that we have built on these windows. And why these windows are important for astronomy as well, because if you look at IZ numbers, we actually have all those lines shifted into near infrared, and that's where it becomes important. And we also have to deal with background skylight that is coming up here, and we have to filter that so that we can actually observe very faint science light. So I show you a cartoon here that shows the downstream of the photon traveling from the telescope all the way to the detector. So that's where the photon starts and that's where the photon ends. So everything in between is what we do. So we have to deal with adaptive optics for sure. And we have to use adaptive optics because if you want to couple light into a single mode or a few mode waveguide, whether it be fiber optics or photonics device, you actually have to correct for the atmospheric turbulence. Done? Now, since I say fiber optics and photonics is invariably single mode domain. So I had to move from a multi-mode domain to a single mode domain, which means I have to use a device that distributes a multi-mode structure into multiple single mode structures, which is called a photonic emitter. I'll come to the details now. Now, once we have this, we have to make sure the sky light is removed. The Earth's atmosphere itself is emitting light in various wavelengths. And that light has to be removed before it reaches the detector. You can remove it once you have the frame from your detector, but by the time it's already too late because you are saturated. So you have to remove it before. And even the removal process is not very clean. So we actually fabricate filters to remove the lines before it reaches the detector. And one good thing is that no matter where you are on the planet, the fingerprint is known, only the intensity varies. You know exactly what wavelengths are going to come. Only the intensity varies. So if you know the wavelengths, you can actually design a filter specifically for those wavelengths. So we do it. And we built a compact spectrograph because now I always believe that once you have coupled starlight into any waveguide, fiber optics or photonics, you should not take it out of it. There is no reason that you should take out the light. So once you are already inside a waveguide, stay there until it comes out of the detector. So we also built a spectrograph based on photonic device that works in waveguide domain, is not in free space domain. So I don't want the light to come out of this free space until it reaches the detector. There's no reason why it should come out. Then we also build frequency comb because why not? Because if you have built a spectrograph, you can also build a frequency comb using photonic component, couple it to a spectrograph chip, which I'll show you. And we also develop our concepts for detectors. Going forward, on the left, I actually show red waveguide ratings. That's the compact spectrograph on a chip. We have achieved resolution up to 60,000 in H-band. And we also started working on photonic issue ratings. We developed beam combiners for more than one telescope. We also fabricate the suppression of OH lines, filters for separating OH lines, build our own frequency combs, and we, of course, have adaptive optics, and we started fabricating photonic lanterns. And based on this, we started developing our instruments. So we built the Potsdam array waveguide spectrograph, Potsdam comb. We are working with our colleagues from Kalaga on developing photonic lanterns for the MARCOT. And we also recently started setting up a Chara array integrated optic test bench for combining light from 4 to 6 telescopes in H-band and K-band. And going forward, so I don't need to explain much about where adaptive optics try to inject light into photonic components. You have to make sure you correct for atmospheric turbulence. Now, I have shown a cartoon here on top here that you see, and you'll see this cartoon and you'll know exactly what part of the chain I'm talking about, the red circle. So I'm talking about photonic lanterns right now. Okay. Now, you have to correct for the atmospheric turbulence, which looks like this. You see the modes jumping around. This cannot be coupled into a single mode waveguide at all. So, if you're looking at a 10-meter telescope at lambda 1550 nanometers, 1 arcsecond seeing, you actually have 600 modes approximately. Same for 1550 nanometers at 10 meters in 1 arcsecond C, you have got approximately 5,000 modes close to. So, you have to deal with that and correct for that when you're trying to couple this light into a single mode fiber or single mode waveguide. So what do? What we do is, you don't need to use extreme adaptive optics. You can actually use lower adaptive optics, couple it into a few mode fiber or a multi-mode end of a photonic lantern, distribute it into single mode fibers, which single mode fibers are not having modal noise. And then you filter that OH lines from that, couple it with photonic component, goes in detector straight off. So, but if you're doing the same thing in space, you don't need to have all that. You can directly couple a photonic component detector because it's diffraction limited. So, injection into single mode photonic components, use extreme adaptive optics in single mode, very difficult to do this. And if you directly couple it to a photonic lantern, you actually have to deal with around 1,000 of modes, which is also not easy. So, what you find a middle point where you couple light, correct it for low orders, couple into a photonic lantern, then they distribute the light into a multiple single mode fiber. And this works perfectly fine. And that's what we do. And what is a photonic lantern? I'll give more details about it. Essentially, it is a structure that converts multi-mode light into multiple single mode light or vice versa. Now, EO basis, I don't need to recollect. I'm just putting it for those people who are not familiar with EO. You actually correct for atmospheric turbulence by using a deformable mirror and a wavefront sensor, find out exactly how the wavefront looks like, and deform your mirror to complement it. And that's what you do. And the deformable mirror does that. Everybody knows this. And we actually set up a AO-based system in our lab to find out, understand exactly what kind of coupling can be done into few mode fibers and photonic components. And that's our system. And we actually have a phase screen that actually can emulate the Kolmogorov statistics that we need. And that phase screen can be used to control the properties of coupling into the fiber, or a P-mode fiber, or a photonic lantern, or even a photonic component to see how it performs and how it doesn't perform right. All right. Now, photonic lantern. This part is main to this talk. So what's a photonic lantern? Connects a multi-mode waveguide to many single mode waveguides or vice versa with minimal loss, hopefully. When you do this, you always encounter loss, of course. So you have to make sure you can do that carefully. So what do? You take multiple single mode fibers that you see, put it inside a capillary, a glass capillary, and then melt it and draw it into a multimode fiber. Essentially, that's what photonic lantern is. So you first assemble your preform. Thank you. First assemble your preform, and then you melt it down. It could be in the form of a fiber, or you can fabricate photonic lantern in waveguides using femtosecond laser. So you can actually write them. And people have done this, and it's well done. And Rob Thompson is leading this effort from Harvard University. So we work with him closely. So, curious case of, so now if you go back to this, here you actually see that you're trying to pack cylinder inside a larger cylinder. So how does this packing work? Is it all packing, does all packing work? You don't know. So let's find out. So we did some, postdoc John spent some time understanding this. So if you take a capillary, which is around 400 micron, and how many fibers can you fit inside this? Like this. This is the best type packaging you get, hexagonal 7 fibers. Only condition is, if you want to make sure the light is confined, you have to make sure the capillary has a refractive index smaller than the cladding. And the cladding, of course, actually has a refractive index smaller than the core in that order. So how do you pack? Can you pack 3, 7, 12, 7, 19, etc.? Are all packings good? Let's find out. So, simple packing question. So if you have a diameter D1, you're trying to fix it into D2 or D2 into D1, then the packing density is given by this equation. And what we found is that as you increase the number of circles you want to pack in, you start noticing a certain pattern coming. And then we modeled this to understand what exactly the packing will see. You start noticing certain density peaks. The packing density is better in certain numbers. And that's what you see. So you can do 7, 19, 27, 37, and 61, perhaps, yeah. So not all combinational fibers fit into a circle. So there are some which actually pack very good. When I say very good, what do I mean? So here you see an N×4 multimode to multimode photonic lantern packing. But you see this kind of setting where you have 6, 11, and 18. These are unusable because you start noticing a lot of gaps here. And these are dangerous because when you melt it and draw it, you'll start catching air pockets, which are going to be very difficult for you to, and it will deteriorate the performance of the lantern. The throughput will be bad. So there are certain usable combinations which you need to use. That's what we understood. And here you see N is equal to 7 packing. This is a lantern that we made. And here is 19. We also made 37. And if you watch closely with 19, we cleaved the fiber just before it was fully fused. You can actually start seeing that you have certain gaps which will fill in as it goes in. And this is actually important. So when you're making the lantern, because it's a melting process, the cores don't stay there, they slightly move around a little bit. This is also important because it causes losses in your lantern. So we studied that also carefully. I'll show you how these lanterns are made. So this is what we do. You take a capillary, stuff it with fibers, 7, start drawing it, melting it down until the cores are too thin to confine the light. So when the cores become thin, as you draw them, the light escapes them, escapes into the cladding, and the cladding becomes the core now. The capillary becomes the cladding. That's the photonic lantern. So you want to make sure the light escapes from the core, comes out in the cladding, cladding becomes the core. All the claddings fuse to one, as you see here. This one you see here. That's basically it becoming core. So what are the challenges? So this is the fun part of it. So trying to stuff the capillary single mode fibers into a capillary. If you have ever handled a bare fiber, you know how notoriously brittle it is. So sometimes you don't get it very carefully. It's not visibly possible, so you have to be very careful feeding the fiber into the capillary. And then the fun part. The fun part is when you put the capillary, you crush it. You'll restart again. Sometimes you burn the capillary when you're drawing it. Sometimes after you do everything all perfectly fine and you hold your breath, you notice a crack. There, and say, damn it. Go forward. You burn because you use the wrong powers. The capillary actually has so much undulations, you create a problem. you're frustrated. And after that, sometimes you have a kink, which is, you don't know where it came from. The system might have behaved in a random way. And that's also a nasty thing. You can actually see that this is going to be a problem. And if you couple light, you can see light coming out from that, which is a bad thing. When you have optical fiber, if you see the fiber shining, you know it's a bad fiber. You should not see light, technically, right? Go forward. This is not visible to the eye. You put it on the microscope, you notice this slight kink. It's going to be lossy. So these things have to be carefully followed. All right, let's assume that you have finally successfully made a lantern. How does the setup look like? This is how the setup looks like, how the lantern is made. You feed the fiber from here, this part, and goes into this. And I'll show you a video. These are the annotated parts. You have a single mode fibers here, holding blocks, filament, vacuum pump, and capillary. The vacuum pump is used because when you want to feed this fiber into a capillary, you have to use isopropyl alcohol to make sure the process is smooth, and then you use a vacuum to pull out the alcohol while you are melting it. If you don't do that, alcohol is going to evaporate inside and create bubbles, and it's a nasty thing. So let's see if I can play this. Let's see. That's the fabrication process of a photonic lantern. This is the first time anybody is seeing such a video. You'll never see the fabrication process of the lantern anywhere. It's 8x sped up. It's sped up 8x, 8 times faster. It actually takes a long time because the drawing process is very slow and very gentle. You're done. Happy. Got a lantern. Very good. Now, you find out what kind of post-tapering we need to check. So basically, you have to find out when you're pulling it, how hard are you pulling it? So essentially, you have to make sure you give the right tension while pulling it. You don't want to pull it uniformly, but you actually have to pull it in a structured way. Is through what experience and taper rate. So when you pull that too fast, tapers fast. You pull it slowly, tapers longer. So you need to control the taper ratio also very carefully. And we actually studied what taper is suitable for what losses, for what wavelengths. So we did that. Okay, now you have done that part of it. The next process is understanding the taper rate, which is what we have done. And we also sent our lanterns to a company in Sweden who also did this work for us to understand what kind of taper rate we got. This is our taper rate that you see here. And here is their taper rate, and they actually measured that. On their system. So you can actually see the measurement, taper measurement being done. This is important because you need to understand that taper is uniform and it actually has got structure. It's not undulating, so it's a problem. So you have to make sure you quantify this and qualify this better. All right, that's good. Now I have got the after all the effort, I got the photonic lantern. Now I need to cleave it because I want to splice it to a patch cord, a multi-mode patch cord. So now you want to how to cleave this problem. This is not also an easy thing. Unlike standard fibers, cleaving taper is challenging because the compound structure, partially fused material, and tapering profile, possibly occur microbubbles and bends. So what do? So this is a video we took at AIP of how the tapering is done. You notice it's actually pulled and you're gently approaching with a diamond tip to break it. There you go. Perfect taper. It's not always safe. Same with our company in North Labs. They have also done the same process that we have done. They also have a system that can do this, capable, and you actually notice the load here. The fiber is under strain of 90 Gs, 90 grams, and it's actually pulled, and the moment it breaks, it becomes 0. So the tapering process is not an easy thing. You can't use a simple fiber The cleaving process is not simple. So you can't use a simple cleaver. You have to use specialized cleavers for this. So this is something we have to learn to modify how to do this. And you're jogging the anvil now. He's slowly jogging the anvils, approaching the fiber very carefully, and then he has cleaved it. I can see the load became 0 there. And you have cleaved that. That's perfectly fine. All good. Sometimes it looks good to the eye. Look it under the microscope and you know it's nasty. So this is a multi-mode to multi-mode photonic lantern. Good cleave, bad cleave. So this is a problem. So this is going to cause problems for you when you use it in the downstream. It looks very bad sometimes. Could be like this. All right, now comes the second fun part of it. Because the taper actually has a diameter, your patch cord that you buy from a company actually has a different diameter. So the diameters have to match. So how do you join these two fibers together? It's not an easy task again. So the process looks like this. You can see the video. This is a splicing process of combining two dissimilar fibers together. This is how it looks like. And then you heat it very carefully to make sure it melts evenly and fuses together. That's good. The fun part. Splice too cold, splice too hot, splice in too far, imperfect splice, offsets. So this is where we learned how to do it carefully because we had so many failures. We understood the types of failures and we actually found out what you should not do. So we finally got it, the perfect splice. After all the efforts, we learned what should be done to get the right splice. And now you have to make sure that the core of the tapered end matches the core of the multimode fiber. As long as the cores match, claddings do not match, you're fine. And then you have a photonic lantern. And this is basically the index construction. You can actually see a little bit of core still remaining, but they will not confine light. They will just escape and fills up the cladding. Fills up the core region, which has the original cladding part of it. And then comes the step of characterizing. So you want to understand throughput, common dispersion, mode of noise, focal ratio degradation, so on and so forth, which are not known for photonic lantern. So you need to work on that. So we are building this for the MARCOT Pathfinder. So as most of you already know what MARCOT Pathfinder is, we are working very closely with IAN as well as Claralto for this telescope, which is going to be connected to the harmonies to see whether we can do follow-up research, follow-up studies on exoplanet research. So the concept is hunt and chase. The big telescopes that are expensive to build will do the selection of candidates, and the smaller, affordable telescopes can do the follow-up research and do very dedicated studies of those candidates. That's a point. So if you look at how many hours how many euros per hour you need for a telescope, typically for 10 meters, you need spending 100,000 euro per hour at an observatory, right? Is that how expensive that is? So, but with this kind of designs of telescope, you can actually make it really low cost. That's the point here. And we are looking at the future 5 and 10 meters telescope in the future to enhance the capabilities of Kalaga Observatory. So all our keys point to the same target, two operational modes, imaging mode and spectroscopic mode. And the idea is to have a bigger module that can do hunt and chase. So we have the Pathfinder, which is 7 modules, and the idea is to have wider one. So this is a animation of how it should conceptually looking like, basically. All right, so there's a good video on the advertisement from MARCOT and what we are planning for in the future, and what is the current setup of the system we have, and yeah. All right, so for now we have the MARCOT Pathfinder located close to common spectrograph, but in the future we would like to take it to little bit more, many more modules that also connect to the common spectrograph. So we can actually do multiple lanterns connecting to each of these modules, feeding the common-rays spectrograph, for example. So that's the idea. Okay. So because it's a modular structure, it's 1 order of magnitude cheaper than large telescopes of the same primary mirror. And it's easier to operate, easier to maintain, replace. And because you have single individual OTAs, you can actually do much more than what you have a single primary mirror. And it's a segmented telescope. Not a segmented mirror telescope, telescope. Yeah. All right. So this specific Pathfinder uses a novel kind of photonic lantern, not your traditional photonic lantern, which is single mode to multi-mode. But this one, in single mode to multi-mode, you actually see that the cores are too small to confine light, and the cladding becomes the core. But in multi-mode, novel design that we started doing, the cores still exist, but the claddings are small enough too small to contain the light, basically. So the claddings become thin, and the cores still exist. Cores fuse together and become the multi-mode end of the multi-mode lantern. So that's the idea of multi-mode to multi-mode photonic lantern, that you use the fibers where the core to cladding ratio is very small. You want the claddings to disappear, and that's what we have done. First proof of test we did with 4 fibers. You can kind of see the cladding still in between, but it's no longer capable of confining the light. So light just comes out. And here you can see the complete cladding lighting up, and the capillaries around this is containing it. And you can actually see that in the refractive index profile, you can actually see the slight cladding still existing, but it cannot hold the light anymore. And you have this gigantic core, which is your multi-mode core. And that's what we have done. Now, going forward to OH emission lines, everybody knows where the Menon lines come from. You have a layer of hydrogen interacting with ozone at an altitude of 87 kilometers, and the whole layer is about 10 kilometers wide. And you actually have this interaction that creates OH hydroxyl ions, which actually have very short life. But in that process, they actually have different vibrational bands, and each of these vibrational bands actually emit different wavelength ranges. So you can actually have K, J, H and J band and visible band as well. So this Earth's atmosphere actually emits this light, which we can't see, but the spectrographs definitely can see. And if you look at the spectra of Earth's atmosphere, it actually looks like this. And this is a fingerprint of Earth's atmosphere. No matter where you are on the planet, it will be the same. It's just the intensity changes. So you know exactly where the lambda is, and you can actually build a filter for this. There's a 2-mass experiment that took a video, a 9-hour video, accelerated. You can actually see the sky moving band. But what you're seeing here, these are not clouds. These are emission in J and H band, J and K band. These are light emitted by Earth's atmosphere. These are not clouds. For the visible lights, completely clear sky. And the spectrograph will definitely see this. This is a problem. You have to filter this out. And these lines, you need to carefully understand how the lines actually look like. They actually have a Lorentzian white line shape. So it's not easy to make a filter for such a emission line. And if you have this kind of 2 lines too close to each other, the interline continuum is very poor. So typically what they do is if you have 2 lines close together, you join that into one filter, and you just lose the science light between them. But that's what it is. And these line properties change during the day and during the season, during the year. So it's intensity constantly varying. And also the full width half maximum. The full width half maximum also constantly varies. Lambda is the same. So how do you remove these lines? One concept that was published in 2012 and proposed was using fiber Bragg gratings to remove these lines. And this could be either in fibers or it could be in waveguides. So you can actually create a layered structure that can remove this. So you have this light coming in, which is science light plus OH lines. You want the OH lines to be rejected and only transmit the science light. Such a device can be done in a fiber or in a waveguide, either by controlling the refractive index or controlling the ineffective of the waveguide. Either way, you can do this one. But this structure can only remove one OH lines. But if you want to remove that fingerprint that you saw, you would think that I can make a series of these gratings and I can do a job, but no. A series of gratings like this is going to be extremely lossy for a science light as well. So you can't have an array of reflecting surfaces in your path. You actually have to have only one. So what do? You actually create a complex index grating that can actually, in one go, select emission lines from OH lines. So that's what we do. We actually fabricate these structures. And we can do it 3 different ways. One, because you know the lambda where it's going to come, you can create a diffractive optical element that can imprint a filter structure into a fiber, and that can filter out these OH lines. You can fabricate. So we designed this complex space mask, this world's first complex space mask that can remove OH lines. Our colleagues from Fraunhofer. The second method we use is more customizable and tunable and flexible, is what is called as a running light interferometer or modified elliptical Talbot interferometer. Basically, it's an interference pattern that's moving. I'll show you how it looks like. And you can also inscribe these gratings in fibers, line by line, one layer at a time, using femtosecond lasers. That's also something we do. And then you can, once you create this filter, you can create a filter like this, which is basically the OH line filter you want. And okay. So imagine this kind of structure. Imagine this is your interference pattern that's moving, and this is your optical fiber that's moving. So if you have an interference pattern that's moving, an optical fiber that's moving, you can actually imprint the interference pattern onto the optical fiber as it moves. Now, imagine a situation where the interference pattern and the fiber are moving at 2 different velocities. What is going to happen is you're going to create a Doppler shift of the pitch that you inscribe in the fiber, and you can actually control the speed at which the fiber moves to write a very complicated structure in the fiber. That's your grating. And this is an example of the process that's happening. And you see that vibration that's happening because I'm walking around with the camera. So it's a very sensitive process. All right, so the fun part. The fun part is that I move, the interference pattern shakes. So it's that sensitive. And why it is sensitive? Because I have to make sure the interference pattern is focused on a core of a single mode fiber, which is around 4 to 10 micron, while the fiber is moving at 100 micrometer per second over 20 centimeters. So what kind of a translation stage can achieve that kind of precision in X, Y, Z, pitch, roll, and yaw? So we actually have to design a custom translation stage that can do this. So we have got a stage that can actually do this kind of accuracy, 500 nanometers and 1 micron XYZ. Incredibly stable over, actually it is designed for 50 centimeters, half a meter. We only use 20 of it, we don't use all 50. So this was also custom made, and this interferometer actually has its own interferometer that corrects for the room vibration, room temperature, and room pressure. So all 3 are monitored, and if there are more people walking into the room, the body temperature can increase, the room temperature, that's also corrected in the interferometer. And that's the only facility that we have in Europe, as far as I know. So you can actually remove these lines before the light reaches the spectrograph. You don't need to use software to remove the OH lines in your frames. And we have published with our colleagues in Australia primarily. And there's an example of what happens when you have such a filter and you can actually bring down this background of a detector very low enough to detect very faint sources. Okay, now move forward here, you can see I have moved forward from filters to spectrograph here. Okay, now, like I said in the beginning of the talk, that my goal is to decouple the size of the spectrograph from the size of the telescope, right? How do you do that? So if you can couple all the light into optical fiber, no matter the size of the telescope, and once I have it into the optical fiber, I connect the optical fiber to a photonic spectrograph on a chip, and I do the job. I don't want the light to exit the fiber anymore. So a photonic array waveguide grating is one such device that uses interferometric methods to actually segregate wavelengths. And we actually have custom designed this spectrograph on a chip and fabricated in a foundry in less, and we have multiple chips here. And around this chip, we build our spectrograph. And this, for example, is a spectrograph that can go from 10,000 to 60,000 in H band, resolving power, a very, very, very low losses. And because this material can actually take more, this design can take more than one fiber. In this case, I can attach 15 fibers to this. So technically, I can attach a photonic lantern from a multimode fiber to this chip, and you actually can access all the light coming from the telescope. And that's what we have done. And we have done many innovations in this one. It's not an off-the-shelf component. We actually cannot use array wave gratings that are usually used for telecommunication, which are not suitable for astronomy. So we actually had to design a different design. For this case, we have a design. We can, in a single chip, you can actually achieve different resolving powers in a single chip. This is the one innovation we have done. The second innovation we have done is to optimizing the grating pitch so that the throughput is very high. This is unique. Third innovation, and we see the performance of system with and without those modifications, why the throughput increases with this design. And here we have symptoms of fabrication errors. So because it's a photonic chip fabricated in at a foundry, their systems actually can achieve certain resolutions, and their resolution actually impacts us. And we actually studied how a given foundry's capabilities actually affect the performance of the AWGs we have. And what we found is, as per the current state of the art, if you have the best foundry for fabricating the best spectrograph on a chip, the highest resolution you can achieve is 650,000. That is the highest theoretical resolution you can achieve given the current capabilities of the foundries. Now, foundries cannot always do that, so you always creep in some errors. Those errors actually reduce the resolution down to 80,000, basically. That's how bad that is. So we can achieve 80,000. We didn't try. We stayed at around 20, 30 resolving power, 30,000 resolving power. Okay. Now you have your AWG that can actually do resolve your starlight into multiple wavelengths at very high resolution. One problem is with AWG, you actually have the light coming out at in an angle, a curved angle, and that's going to create a problem. So you see the light is focused along a curve that's called Roland circle. So the light is focused along the curve, and when you cut this chip so the light comes out of the chip, you actually cut it in this direction like this, which means in this corners the light is in focus, but you actually have a defocus aberration here. So the current designs, the traditional design for AWG is not suitable for astronomy. However, we have used it. So we did an innovation there also. So the innovation we have done is, instead of having a curved focal plane here, we actually designed AWG with a flat focal plane. So you don't have a defocus aberration anymore. So this is a thing. So if you have a curved focal plane here, you'll notice that at the center it is defocused, but in the corners is focused. That's what you get from such a design. But with this design, you will not see that. Now, once you have this, you can see this one actually is curved design. So you actually resolve the resolution changes as you change your wavelength as well. But in this case, the resolution stays same for all wavelengths. So this is the innovation. You can see it is flat here. And we compared with our performance of other groups who are working, and we know that we actually can do very good resolving power, very high resolving power at a very low loss. And we have done so many designs of this spectrograph on a chip, various shapes, various designs, and various resolving powers we have tried. So it's a full work actually. And once you have that, we build a spectrograph around it, ground up, completely new, including the cold plate design, cold finger design, radiation shields, cold optics, cold stops, warm stops, sapphire windows, filters, everything. Gitter, cross disperser, everything completely designed ground up. And this is the spectrograph actually we designed. And here you have your AWG spectrograph on a chip and your chip here. Now, question is, if you already have a spectrograph on a chip, why do you need the rest of it? You already have a spectrograph on a chip. So why is your spectrograph already so big? So we actually deliberately built it this way, because if you see, the chip is sitting here outside, not inside, it's sitting outside. and the rest of the cold optics is inside. We designed it such as because we want to change different architectures of the chip here so that the rest of it remains same. So we actually have that freedom for the first Pathfinder, as you say. So we build it this way. But in reality, if you want to build a usable spectrograph, you can actually put the chip inside and compress this whole thing down and make it really small. And that's where we have built everything. And Alan and Eloy, our postdocs, who actually helped us to build this. And you can see the cold plate here. And the trick is aligning the optics while it is cold. And then we studied how the different parts of the spectrograph descend. We can actually check the temperature at different locations of the spectrograph to find out where exactly the detector is. And we used the H2RG, Hawaii 2RG detector for this. It's at 80 Kelvin. And this is one such example of using a different wavelengths pointed at it. And we actually studied how, if there is any misalignment of the cross disperser to see the circle, it's supposed to be a circle, it becomes an ellipse because of the geometric distortion that you're seeing. And after all the alignment, all the focusing and everything perfect, a chip that was designed to be 27,000 resolving power, end result is we got 10,000 resolving power because of the defocus aberrations and all coming from the free space optics, which is what the problem is. I don't want the light to exit the chip. Why should it exit the chip? It should stay in the chip. So can we do that? The next stage is basically what is called as Cosmos, which is actually a second version of the simple set. Instead of using one chip, if I have a photonic lantern that has 19 fibers, why don't I connect each of these fibers to each of these waveguides, and I can actually use all of the chip. I'm just using right now one, but I can use all the 15 waveguides. And I can build a complicated structure like this, a multi-object spectrograph, for example. So I can actually create an IFU with fibers, and each photonic lantern distributes in one multimode fiber into 19 single mode fibers. And the single mode fibers from the photonic lanterns can be distributed across the AWG. So one fiber comes here, the second fiber goes to the second one, third one goes to the third one. I can do that. So which means each AWG can actually access one particular wavelength, the AWG2 can access different wavelengths. So I can get the spectrum of the same object in different wavelengths at different resolutions in one go. So this is what we are right now building. Right. So that's exactly what we do. And here we can actually see whether this light can be coupled in, can use the entire real estate of the detector. And we can actually assemble the orders of the AWG into the detector very carefully. So we can see which AWG, which light comes where. So we can do this. So this is what we are building right now. For space applications, there's no doubt about it is suitable for space applications, because if you look at, for example, I took an Juice and Magis spectrograph for ESA, which is actually having resolving power of a few thousand, a few hundreds, basically, very low in this spectral wavelength range, and it's quite big. But you can replace that with this. And it is in space, diffraction limited. So what we found out is, can I make it really small, even smaller? So yes, for silicon and silica, we found out an X factor that is important. If you make sure your resolution of your chip is around 2000, you can actually achieve a wavelength band of 300 nanometers, and you don't need cross dispersion. You can put the detector right at the output here. Such a detector right at the output, and you got your spectrograph. So the spectrograph could be the size of a shoebox at a resolution of 2000. Slightly larger than 2000, if you want to go, the shoebox becomes bigger, but it's still smaller than this. Moving forward, we also built our own frequency comb, and the best we have achieved is 25 centimeters per second radial velocity stability. On a regular basis, we achieve 80. Some good days, when we are feeling good, we achieve 50. And some of the perfect days, we achieve 25. So this is based on a micro ring resonator device with 4-way mixing. And you can see here one of my postdocs holding the chip mounted on an electronic board, which means this frequency comb tower can be at an observatory connected to internet, and I can actually sit in Potsdam and control the properties of the frequency cone because it's computer controllable. And that's how small the chip looks like. That's all you need to create a. And by the way, this chip here, this actually has 8 different frequency cones on it. I'm only showing one of them here. And I have 99 such chips. Essentially, I have 800 different combs of different FSRs, different ranges. So I'm not going to details of this, how the comb is built, but you're welcome to ask me. We did a strange experiment. In our institute, I have my frequency comb in this building. I have a spectrograph in this building. So I use the institute fiber network to plug in the frequency comb here and take it out there and plug it into the spectrograph. The point of doing this is I can have a comb far away from the spectrograph because it's fiber comb. You don't need to be near the spectrograph. That's what we did. So I tested the comb over 22 kilometers of fiber. No problem. It works fine. Only loss of power, but it's still strong enough and very stable. No chromatic dispersion. The fibers, the modern fibers that you get are really good. So you don't have this kind of wavelength problem. So second thing we did, we converted one comb to 4 combs. You can use a simple device like this to distribute the comb into 4 combs. So now I have 4 frequency combs from one comb. And it's all fiber coupled, which means all of them go to different telescopes if you want. And distributed, it can be far away. And the next work we did is photonic beam combiners for La Palma, where we combine light into a photonic chip. Unlike the photonic chips that you saw till now, this is a photonic chip that is fabricated with a laser, and it is a 3-dimensional chip. It is not a 2-dimensional chip. The gravity beam combiner is a 2-dimensional chip, right? It's planar. But if you want to make a much more complicated interferometric circuit, your chip becomes bigger. As the chip becomes bigger, you start having fabrication errors coming in. And those fabrication errors manifest as phase errors in your interferometer, which you can't do anything about. So you can't make the chip big. You have to keep the chip small. So the only way you do it, go 3 dimensions. And you can't do photonic 3 dimensions except with ultra-fast laser inscription. And you can actually see this tiny waveguides here. And by the way, there are 1, 2, 3, 4, 5, 6, 7 or 8 different beam combiners in that chip. And it's a 3D beam combiner. So you can actually couple light from 4 different telescopes, or you can couple light from the same large telescope. You can do people mapping. Different parts of the primary can be coupled together. That's what we did. And that's what this looks like. So as the path lengths are varied, you start seeing intensity variation, and those intensity variations can be related to the phase variations in the telescope, and you can build a high resolution image of the star. And we saw the first light in 2019 in William Herschel telescope. And this is a setup where different parts of the primary mirror are coupled into the beam combiner, and that's what we did. So we went from J-band, H-band to K-band, and we moved to Chara array, and we are building a beam combiner for Chara array. And this is a beam combiner that was developed by Harriet University, and we are setting up the complete interferometric optics here. And we actually have series 1 coupling lenses, and you have the beam combiner sitting here. And this is K-band, but it is in the warm. We will be taking this to the cold in the future. It has to be in the cryostat. It can't be in the warm. But this is for the first test, and we are trying to see whether we get light. And we got first light in May 2nd, I suppose. Yeah, May 2nd we saw first light. It came magnitude 4. Now we are taking it to 4, and in the future we take it to 6 and build the cryostat. And we actually have got a telecentric lens for scanning and coupling light into fibers automatically to improve the throughput. And the 4 optics of the series 1 camera were converted from H-band to K-band and from F4 to F280. And that's basically the presentation I have. And here I'm showing pictures of the first generation of these devices. And if you have questions, please to ask. Thank you.
Thank you so much, Robert, for the interesting talk. Any question?
Please don't ask. Please ask.
So, yeah, thank you for this. I see that there's a lot of development that's going on there. So, one basic question is, are these being tested out in different observatories?
Yes,
Or-
yes. The beam combiner is right now, one of my postdocs right now as we speak is in Pasadena. She's setting up the four-telescope beam combiner set up there in Pasadena. In 2018, 2019, we tested in William Herschel telescope. And we also have a telescope at Babelsberg in Potsdam. And as we speak this week, my colleagues are testing for OH line filters for that. And that is connected to the spectrograph that I showed you. So we'll test the spectrograph, we'll test the photonic lantern that filters all together, including the photonic, including the frequency cone. So all will be tested together in the telescope that we have. Once it's working, we will be shifting it to a bigger telescope, see how it performs there.
And how soon do you expect this to be?
It's going on. My postdoc has gone to Potsdam, to Pasadena on a 4th expedition. So it takes a long time to do this. It doesn't happen in months. It takes probably a few years to do this. And you have to set up this, you have to make the alignment and set up in the morning with a local 6 telescope simulator in Chara, for example, STS. And then you wait for the night to come and you have some time before the Mirkex or Silmaril people, they said, okay, it's free, you can use. And then you can use the telescope. So you are sharing with other groups. So it takes, this process takes time. And once in a while something fails, you have to replace it, something doesn't work, you have to replace it. So with beam combiner, we made good progress because we have started working together with a lot of experts in Pasadena. And with OH lines, we are testing it this week as we speak. And photonic lanterns, we have fabricated many right now. And we will soon shipping it to Colorado to test it on MARCOT. And in the coming months, we have few experiments, few tests happening. If they are successful, we will scale up the TRL, technology readiness level, to be a facility instrument instead of a visitor instrument. So that's a different ball game altogether. So.
More questions?
Yeah. Thanks, Kalaga, for a very interesting talk. So after this, after seeing all the developments regarding photonic technologies and imagining how this can be applied to space missions, for instance, or for astronomical space missions, how do you envisage how satellites missions are going to be in the near future when they start using, because I guess this has not been applied yet to any mission in space right now.
Yes, you're right. So thank you. So photonics has really not entered into space applications yet. Maybe the reason is because we have to test the radiation performance of these devices in a proper environment to see how radiation affects these devices as we go, how the radiations affect the fibers, and how the radiation will affect the fiber to chip couplers, whether they can withstand the G forces in the ground-based test, whether they can withstand the vacuum and harsh environment of space, which is radiative, as well as high temperature, low temperature variation. So these have to be tested on ground first, and then it can be tested on space application on a very quick high altitude balloon studies or something. But I know for sure that we actually have a group in ESA who are also working closely to follow photonics for space applications, especially for Earth observations, looking at atmospheric sounding, carbon dioxide. One of my master's students actually recently defended a master's thesis. She is just starting a PhD in November with DLR. There's a German Aerospace Department Institute. And they will be doing some high altitude observations and using some techniques. So there are some studies going on in parallel as well.
So I guess you need services, you need facilities where they can provide, for instance, this service of putting these devices into an environment and radiate the devices with radiation, different types of radiation.
Exactly. So they should do the same thing they would do for a standard optical bulk optics system that goes to space. They would do the same thing for this. So they should follow the same. It should pass the same requirements that passes for that. As long as it passes the same requirements, it should be good. I think no one has done that yet. No one has done that. And it'll be interesting to see because these are low-cost devices, right? And you can replicate them very quickly. So, yeah.
More questions? Regarding this spectral on a chip, do you really think that this is going to be a substitute of the traditional spectrographs?
No, it won't be because traditional spectrographs can access much more of the PSF of the telescope you have. But my point is, it need not replace existing spectrograph, but it can replace, not replace, it can, like I said, it can be a support spectrograph, I would say, that can actually do the same thing at a higher resolution with less coupling into the chip, but it will not replace Ishals, for sure. Ishals are required and people are happy with Ishals. But specifically for space applications, these are better than Ishals. And this can't replace Ishals. Ishals can't replace them. Especially if you have, for example, Mars rover or something, where you can have a spectrograph sitting at a very high resolution. I can achieve 100,000 resolving power with this, and you can't do that with the Ishal. Ishal is going to be very difficult. It will be bulky, it will be heavy, and the launch process is going to be difficult for that, or alignment is going to be difficult. This is much more suitable. For example, if you look at NearCam or NearSpec, for example, their resolving power is low compared to what this could achieve. And you're in diffraction limited environment already. So it could have been a photonic chip, right? So, and you would do what you're doing at 9,000 resolving power, you can do it at 30,000 resolving power in diffraction environment. So for space applications, excellent.
And how complex in terms of time and also budget?
So I know for a fact that there are colleagues who are working on CubeSat projects, and they are testing the performance of compact photonic-based nulla interferometers and beam combiners in space for a CubeSat project. That's the first beginning to understand what are the parameters is going to influence here. We are now embarking on a project in the next 4 years to really make this smaller, specifically for space applications, to see whether the chip, the detector, the fiber, all can be put together in a very tight form factor with no moving parts or no bulk optics in between, so that it can be, it can pass the rigorous tests that typically a space module goes through. So this is something we, in the next 4 years, we are going to embark on, focusing on space applications specifically. I think it will take at least 5 years before we see a conceptual system in space, at least. Yeah.
Someone else? Okay, so we thank again to Kalaga for this fantastic talk. Congratulations for all the four and all the nice experiments.
Oh, Michael, I had to pass on the congratulations to my colleagues. It's their work.
Thank you so much.
Yeah.